Can you all hear me? Try to turn that bell off. Well, just for the record, I've got the thing on mute for this chime, but it's still chiming. I don't know what else I can do. And I'm assuming you can all see this paper. Can you hear me okay? Anybody? Can you hear me? Okay, good. Thank you, Matthew. If you want to turn your cameras on, great. It helps me, but I understand. Some people are having lunch. Some people are probably in their pajamas. Some people just want to be left alone. Okay. All right, let me start early with an office hour sorts. Does anybody have any questions about the homework problems assigned? Solutions, anything like that? Today, I'm planning to cover complex power, and then if time allows, three-phase power. Anybody at all? Nothing? I think in the best interest of everybody, we should at least do one problem. And let me get one note up here. It's Friday, it's a quiet class. Very few people. I got Joseph's on, but I don't see anybody else. How many people do we have? 19 only. Okay, well, it's still early. Just coming up or not? So I gave you problems 24 through 31. I'm just going to show you what I'm talking about when I go through them, see if there's any problems. I want to do now. We're getting more people. How many? I know it's Friday, so we only got 33 out of 93. So we're missing 60. But if you don't mind, I'm going to start now. It's about 1 o'clock. All right. Now, anybody have any comments, concerns? And if the internet's been causing a problem, I understand. I had some trouble with it too. Is anybody here experiencing any internet difficulties or difficulties with Canvas or anything like that at all? Anybody? No? Okay, good. Well, great. I hope you're having a good Friday, and I wish I could shut that thing off, but I can't. I've tried. Just got to live with it. All right, I'm going to do 528. Now I'm showing you 528 here. It says calculate the voltage Vs. That's here. Let me try to blow that up. Y'all follow me on this, class? I'm trying to do this problem right here. Can you all see it? I mean, some signs of life. Okay.
Yeah, we can.
With or without. If you turn your cameras on, it helps me. But if you don't want to, I understand. And I appreciate it if you do. Anyway, if we take a look at this one, now these are simple, in my opinion. You do have to do them, and do them without looking at the solutions. Struggle to get the answer unless you can get it really quick. So here I'm going to just build a problem, and I'll tell you some of the problems that happen with these. I'm creating the drawing, then I'll jump over to here to my camera. So don't worry, I have Vs here, and then I have 30 and J5 ohms. So I'm just redrawing this. And then I have J5, boy, that's aggravating. And then I have a load. And for the load, that's ZL. They want plus to minus VL across it. And I don't know if they want, but I'm going to get IL. And for this problem, they say the load has 2 kW and 240 volts. So this is 240 volts at 0 degrees. And the power factor on this one is equal to 0.8. But notice, this is the rarity. It's leading. I would underscore that, leading. Very rare. It's a leading power factor. I think he's just doing it to mess with us. So we be attentive here. And they want this voltage, Vs. So this is the object of what they want. And they said the power here. Power of the load is 2 kW. So now I'm going to go and jump to this. All right, so I just redrew the problem. Everybody with me? Class?
Yes.
Yes.
Hey, oh, Jessica, I got to make you a co-host. Always yell at me about this. Where are you? Oh, there you are. Make co-host. Does anybody want to be else want to be co-host so you can record or do something? Anybody? You? Okay, Joseph, you got it. Anybody else? If you do, let somebody know and or just unmute your mic. Okay. For this problem, let's do it. And by the way, this is a standard kind of problem you should be able to do. So with this, there's really two equations that we need. The first one is the power at the load is equal to VRMS. Now that is just a magnitude times IRMS. That's the current flowing through it. These are magnitudes times real.
Baginski, you froze.
So what now?
Well, I guess we wait until his internet gets fixed.
Y'all, I cannot.
If anyone wants to
It's
has
still
a doc
recording.
can, wants to pick up where he left off, and go for it.
Did he say anything about when the next quiz was going to be?
No.
I don't know. On Wednesday, he said something at the end of class, like he was going to take a vote or something, so he didn't waste more time before the test.
I wouldn't be surprised if we have another quiz on Monday.
I want to think he said during the last class that he was going to like forego this week's quiz. So maybe we won't have one until like next Friday or something.
Can you hear me? Can you all hear me or not?
Yes, we can.
Or we can't, I don't know what happened. The only thing I can tell you is I was on and then all of a sudden everybody was gone. Did anybody else experience this or just me?
No, it just got froze and then it stopped.
Yeah,
You're close too?
Mhm.
Okay. It has nothing to do with your Zoom stuff. I tell you that. This has been a problem that they've had, an ongoing problem. And I'm not sure if the weather is in some way, shape, or form affecting it. It's hard for me to believe that, but who knows? Anyway, back to this problem. Thank you all for hanging in there, and I apologize again for this. I don't know what happened now. Now, can you see the screen or is it not sharing?
Not sharing.
Okay, it will be in 1 second. It was, the whole thing just shut down. Can you all see it now?
Yeah.
Okay, this is the problem we were about to do when all of a sudden the lights went out and no idea what happened. That's the first time it's happened in this class like that, though. It's happened in others. All right, now for this particular one right here, this is the problem. And they give you this information. So let's see how many people can do this. This is 240 volts, power of 2 kW, and we're asked for this voltage, which is a very reasonable request. So the thing you want to do first and foremost is find the magnitude and then the angle of the current. Do you all concur with me there? Let me see if I can open this thing up. Give me 1 second.
Yeah.
All
Yes.
right, I want you to, if you know how to do that, go ahead and do it. If you don't, well, I hope this doesn't do it. Just hang on. So to get the magnitude of the current, we're going to go right to this equation right here. We have the power factor, right? And it's 0.8 and it's leading. I underscored that in, I think last time Gabriel noticed that I didn't put it when it was lagging as a negative angle for the value of the angle associated with the current. But we're going to get the magnitude of the current from this one. So we can see IRMS here, which is I line, will be equal to the PL, that's the power used by the load, is 2000, right? And then you got to divide it by the value of the voltage, which is 240 RMS. And then it's divided by the power factor, which is 0.8. Now, I don't remember if I did this one its entirety last time, but I want to do it again. Do y'all remember this? Doing it? No? It doesn't matter. Do you all agree that
do.
this is the value for IL's magnitude? Class?
I think you did this problem during your office hours yesterday.
Yeah.
That's all right, but I want to do it now for everybody, and I want to make sure everybody sees this. Got me, everyone?
Can
All
you
right.
zoom in a little bit? It's kind of hard to read some of those subscripts.
I appreciate that. What I'm going to do is do you one better. I'm going to do this. I hope this works. I think that's what I had last time. Oops. Did that change at all or not? No? Anyone?
No
Oh.
change.
No change? Okay, don't worry about it. This is what we got here, correct, class? So we can get the value of IL. Do you want me to do it or can somebody give that to me? I can get Octave going. When I have a live class, usually students have their calculators out and they're doing this before I can ever even mention it. And they're giving it to me. As soon as Octave comes up, I want to get a number here for you. I remember I did this last time, but I don't have that in front of me.
1.04167.
Appreciate that. I'm using Octave for that, just so you know. So I'm going to have PL, or just, sorry, I'm going to have I'll just use it as I is equal to 2000 divided by, and this is going to be 240 times 0.8, right?
Isn't it?
And you got that 10.417, correct?
Yeah.
7, and that's amps RMS. And the only thing I'm doing over here is just recording it. Then if somebody wants to, it'll save me some time. The next thing I need to do is get the angle associated. This is the magnitude. But then if I actually want I line, it would be that value, 10.417. But the angle would be what? Since the voltage is at 0 degrees, and this is leading, right? When we take the inverse cosine of 0.8, we get an angle, and then that angle would be advanced, correct? Because the current is leading the voltage. Does everybody hear me on that one?
Yeah.
The statement says the power factor is leading. If the voltage is at 0 degrees, the current will be at 0 degrees plus that angle. And can you give me that? Was it 36? Anyone?
36.87.
Thank you. So it's 36.87 degrees. Just leave that. And I would recommend you box that answer on a quiz or on your homework. That's something you're going to be going to. Now, the next order of business is this, in case you weren't there for the office hour and didn't get a chance to look at. We're after this voltage, and here's what I'm going to do. I'm going to box this thing right here. And then I'm going to say that there's going to be a voltage developed across here. And I'm just going to call that V line. And what this actually represents is a transmission line. And a transmission line is the electrical conductors that go from like West Point Dam to your house, or frankly, from a power substation to the pole outside your house or your apartment. That's what they mean when they say transmission line. And this represents the losses and the inductive reactance of that transmission line. Now, they are made of copper. You will never see a capacitor here. And if you do see a capacitor in series, they're just doing that to test you. That doesn't happen. Anytime you have current through wires, the reactive nature is inductance, and it'll have a plus J value. All right, to get this line voltage, since we have IL, does everybody agree the plus to minus line voltage, because the current is entering the plus terminal, would be equal to simply I line times 30 plus J5? Do y'all agree with that? We did it last time. With me, class?
Yeah.
I'm trying to make sure that I don't have any stragglers. Anybody that doesn't see this, because I'm assuming you see this. Now that value for V line we can get, Joseph, or does anybody have that? Anyone that can give it to me? I can do it real quick. But remember to add that angle on. You have to add the angle of what? 36.87 degrees, right? For the current. Anybody?
I think it's 458.7.
It is.
Wait.
Great time to try out your calculators. See if you know what you're doing. It really is.
I
Want me to do it over there? Say that again.
What value are you looking for the V line or I line?
V line, we have I line, right? We have this. Can you all hear me?
Yeah.
We have the current and the angle associated with the current, right? So this, it is leading, correct, everyone? In your books, it's leading, right?
Yeah.
Yeah.
All right, if it is leading, then this would be IL times that would be, and that IL value has this angle. What did you get for that again?
Wait, is it?
Not is it? I just need the value. I don't have a question. I'll do it. All right, here's how I get. I'm going to just say IL, or I'll call it I line is going to be equal to I, right? And then I'm going to multiply it by EXP to the 1J times a cosine of 0.8. That's the inverse cosine of 0.8. And that'll be in radians, so I get this. That should be your value of I line if you want it in real and imaginary. Y'all get that, class?
Okay.
Yeah.
Okay, if you've got that, now I take that and to get my V line right here, that's going to be equal to I line, right? And then it's going to be times, and here it's going to be 30, right? Plus 1J times 5. And that's the value of V line. Now the magnitude is ABS on I V line. I don't know, your calculators will have similar functionality. It's just, I don't. So that's the magnitude, and then the angle would be of, if you want this, you don't have to have it. This isn't important right here. And if you want it in degrees, it's times 180 divided by pi. There's probably a single command to get that. So that would be the voltage associated with the line losses. It'd be 316.81 at an angle of 46.332 degrees. Y'all got that, class?
Yeah, I did it on my calculator. That's what I got.
All right, great. And if you're using your calculators, fantastic. The more you use them, the better it is for you. Now, I don't want that. I want VS. So when I look at VS on my drawing right here, I can see that VS, starting at the negative terminal, I know it's out of focus. Come on. Oh, I know this thing's there. So anyway, VS would be equal to this voltage, which is just 240 at an angle of 0 degrees, plus this voltage. So if I go back here now, I'm going to get out of focus here, but I'd say that VS, right? VS would be equal to just V line, which is 240, plus, V load, which is 240, right? Plus V line, and this is what I get in terms of a real and imaginary number. Can you all check yourselves on that? Good. And then remember, that's real. To get the magnitude, it would be ABS of V line, or VS, pardon me. Right? So that would be the magnitude. Do you agree with me, everyone? Right? You guys getting this or not? Am I too far ahead of you?
Yeah.
And then, thank you. And the angle of this VS, and I always put it in degrees because the book does, and you'll see it in degrees almost always. It's that times 180 divided by pi. And if somebody knows the single command to get the angle in degrees, tell me, because I don't think this will work. I don't think that'll do it, but maybe. No. No. Anyway, there should be one command that puts it in degrees, but I don't know what it is in octave. Are you all with me on this? How many got that? You ready for a question?
Yeah.
Here's a typical question on
Okay.
a quiz. You got it right? Thank
Yeah.
you, Jim. Y'all guys, I'm assuming most of you got this right, but I can't tell. And we only got 46 today. I assume it's because there's no quiz today, but there's going to be one on Monday, which is odd that nobody's shown up, but that's okay. They've got the recording. Maybe they all understand it, or maybe they got other things that are more important to deal with. Okay, so that's VS, right? Now here's a typical quiz question. What's the total power, hear me now, total power that's actually used, or there's a word for this. Trying to think of what is the total power loss in the actual, either consumed or used, lost by the system. In other words, how much total power is being used by that system? Both the line losses and the actual load. The load just what? It dissipates power. The line is power losses, but there's a term for that, a formal term. Are you with me, class?
You've got
So what
octave
would it
blocking most of your screen.
How would you get that? Anyone?
Is it just as simple as adding the IL plus the I line?
You don't add occurrence like that, do you? Can somebody help them? What would you do? Wouldn't you just find the power loss associated with this, which is 2 kW, right? We've got that.
Yeah.
And we'd find the power loss associated with that 30 ohms, right? So we'd say the total loss, or the total dissipated power, would be equal to 2,000 watts, that's at the load, plus this unwanted amount, which would be what? It would be the resistance 30 times the magnitude of I line squared. Do you agree with me? And that's I line RMS, right?
Yeah.
Now you'll notice there is no factor of 2 here because we're using RMS values for the current. Do y'all agree with me? How many got that are with me? I mean, even heads nodding, anything like that. If you can turn on your cameras, it'll help me, but I understand if you don't want to. I'm going to tell you that kind of a problem will throw people into a tizzy. Really, I don't believe he asked it. How dare he ask something like that he didn't cover? I'm just showing you the kind of stuff that's, I assume you got, because, you know, losses have to do with the resistance, and the loss is calculated by an I squared R if I is in RMS. Do y'all get that? Now, how much loss is associated with this right here? Anyone?
0.
0, right? There is no average power loss. Very important. On a question, on a quiz, and I'll ask that kind of stuff. How much power loss is associated with each element? I'll put the 30 on one, then I'll put that. And I'll see people give me non-zero values to that because they don't understand the concept. They'll take I squared times 5, and they say, it's got to have something that's got to be it. They're trying to reason their way to a right answer, which will get you in a horrid amount of trouble in this class. I cannot tell you how much trouble you can get into by trying to figure out how to answer a test right instead of solve the problem correctly. Okay, now is there anything else with what I gave you for homework you want covered? I thought that's a pretty good example because that's leading.
I have a quick question on this one. Did you say the total power loss, are you adding it with I line or I load?
I'm not adding the I's, it's the power loss. Remember, it's I squared R. There's an R 30 ohms, right? Plus the loss here is given as 2 kW.
Yes.
Right? Loss is in watts or kilowatts. I mean, power loss. And it has to do with current, but you have to square the current and multiply by the resistance to get the amount of power dissipated by any resistive element. Follow me?
Yeah, are you squaring the current that we found that was I line or I load though?
Yes, they're the same, aren't they? Because this
They're
is
the
a series
same?
circuit. Isn't it a series circuit right here? All elements are in series. The current has to be the same, doesn't
Okay.
it?
Yeah.
Right, and the thing is that all these, this is a simple series circuit. The current in every element is the same. Therefore, if you find the current anywhere, you have it everywhere in terms of its magnitude, right? And that's,
So I might be doing this wrong, but I'm getting that the total power is 5,088 watts, which means that more power is dissipated by the line than the load.
and what does that tell you?
It's a really bad,
It's
a lot of
horrific.
copper.
Yes. Horrific amount of loss that should never happen. If it did happen, somebody at the power company or at the manufacturing place that's being used, it would get fired, because you should never have power loss in the line that even comes close to anything you're using. You follow me? If that happened, there's something insanely wrong with what's going on. What they try to do, and I don't have time for this, they try to literally create an effective load here that will be very large with a power factor of about 1. And I don't want to go that route yet, but do y'all follow me? And I'm glad for that question, because you probably asked the question that many other people didn't know how to ask. So I appreciate it. Now, as far as the other problems, did y'all get a chance to look at them and have any questions about them? They were pretty much the same cookie cutter kind of problems, right? You want to do one more before we move on or not? Yeah? All right, Jessica, do you have one in mind? Or do you want me to just grab one?
There's this one. Wait, give me a second.
Hey,
And
by
that
the
problem
way,
you just did,
yeah.
could you talk about the power factor and the leading and where that came into play again?
Okay, the main thing, Dylan, if you're there, when it says leading right here, it means that the angle, remember, this power factor is actually what? It's cosine of theta v minus theta I, right?
Mm-hmm.
All right, so when we take the inverse cosine, we find theta v minus theta I here is actually equal to 36 point, whatever it is. Did I write it down? 36.87 degrees, right? Now that's the angular difference, right? And what
Yeah.
was said is what? When it says leading, it means that the current is ahead by the amount of the difference in the angle. So theta V here was at 0 degrees, right? That's 240 at 0 degrees by the definition of the problem. And it means that the actual current would have an angle that is positive 36.87 degrees. Are you with me, Dylan?
Yeah.
Now, if it was lagging, and we could do this problem if it was lagging, then this would have what? An angle that would be minus 36.87. Do you agree with that?
Yeah. Okay. Yeah.
That's the difference. And if it was lagging, we'd probably have a much different value for voltage. That's another thing. Because then this voltage, V line, would not be I line magnitude at positive 36, but minus 36. Are you with me? Oops.
Yeah.
What I'm trying to say is this voltage with the line voltage would be something where the current here would be the same magnitude, but the angle would be negative. This one's going to have a positive angle, so there would be less voltage lost in the line, is what I'm getting at. Are you with me, everyone? Okay.
There's 5.31, Dr.
5.31. All right, I'm going to show everybody that. Let me just not flip back and forth to the PDF, and I'm going to just throw the problem in front of you, okay? So 5.31 is this problem down here, if y'all can see what I put here. It's on, you've got PDFs, it's on OneNote, and if anybody has any trouble with OneNote, let me know. Now, I prefer to do it this way. I know I could do it a lot of different ways, but using OneNote circumvents a lot of other problems I've had in the past with Canvas. The other thing is, literally, that stuff's available all the time, period. You got it. This one, it says an industrial plant consumes 160 watts. It gives a power factor of 0.9 lagging. What I would do is underline the lagging part. And they say the line voltage at the plant is 480, the line voltage at the plant. He's assuming the line voltage is where this industrial plant is located. It would be like this voltage right here. That's called a line voltage. It's what's at the plant. This is the power company's voltage. It's the supply voltage at the power company. And always make a distinction if I ever gave you a quiz. So when I look at this one, the line voltage is that. The transmission line feeding the plant is 2 miles long. Okay. The impedance is this. So then they give you the line impedance. Find the power factor at the sending end of the line. So first draw it. Okay. I'm going to draw it now. And you can start with sort of a cookie cutter kind of thing. Just draw it like this. You got VS here. Then you have some resistance. Then you have some inductance. Then you have the load here, just as always, right? This is called a single phase. You have a load voltage there, and you have a current I line, right? And that's ZL. Now, what do we know in this one? It says it's 160 kW. So you know the power at the load is 160 kW. And then it says it's got a power factor of 0.9 lagging, right? Lag. And then it says you got a voltage of 480 at 0 degrees. So the voltage here is 480 volts at an angle of 0 degrees, and everything's in RMS. So this is RMS. Okay, right there. They want to know what the power factor is here, and they give you a resistance of 0.1, and they give you an inductive reactance of J0.2. Are you with me? Same template as before, correct? Let's go ahead and get this stuff. Can you help me here and just use your calculators to get this for me? It'll help things. You've got calculators. Let's go ahead and do this. First thing I want to do is find the magnitude of the line current, which is the IRMS going through here. And again, maybe I should put this up one more time. P at the load, the power that's used by the load is V at the load times I at the load, or VRMS, IRMS, times the power factor, right? So I can say that what I want is I at the load magnitude is going to be equal to power at the load divided by V at the load, and the power factor. And that's 160 times 10 to the third divided by 280 or 480. I'm sorry, 480, and the power factor 0.9. And can somebody just give me the magnitude of that?
300.
300 on the nose? Say that again one more time. Anybody? I can't hear you. Could somebody just tell me? You're muted, Joseph, if you're trying to say something.
370.37.
370.37. All right. Do you all agree with that, amps? Or not?
Yeah.
I'm
It's
looking at concern, huh?
Wait, I got 300. Wait, so we have to do wait.
Here, let me do it.
160,000 divided by 480 times 0.9. I'm getting 300.
Let me do it for you. 160 e to the third, right? Divided by 480, correct?
Yes,
Yeah.
times
And
0.
it's times the power factor of 0.9, right?
Yeah.
Yeah.
So I'm getting 370.37.
Yeah.
All right. Now, as far as the angle, I have to take a cosine of 0.9 and 0.9 and then times it by 180. If somebody knows the trick here for a single function, I'm not going to look it up right now. Tell me. I got 25.842 degrees. So this is lagging, right? That's what it said. So this is actually it's going to be minus 25.842 degrees. So this is going to be minus 24.842 degrees. Do you agree with that, everyone? That current, everything's in series, right? Right? Now that current, remember, is everywhere. It's here at the source, it's here at the load, through all the elements. It never changes, magnitude
Wait,
and angle.
you got that angle wrong. It's 25.842.
You're right, 25.842. Thank you. 25.842 degrees. Y'all got this, all right? And it's minus 2, right? Because it's lagging. Y'all agree with that, class? Everybody? I mean, are y'all following me? I appreciate if just some kind of affirmation helps. I'm looking at Darth Vader, a gerbil, and the rest just names, plus the top row. And thank you for having your cameras on. It's a very odd feeling I have. Anyway, that's IL, right? Now I want to get VS next. Do you all agree that that would be a logical thing to get the power factor? I need VS and I have to see the angular difference between the current and the voltage, right? So
Wait,
how do I get?
How did you get that angle?
Inverse.
I took the inverse cosine of the power factor, right? Isn't that the whole idea of power factor? It's the cosine. Power factor is cosine of theta v minus theta I, right? And because that the cosine's an even function, so it doesn't tell you if it's a positive or minus value in here. So when they say lagging, it means whatever angle is associated with the voltage, the angle of the current is less than that. And the angle with the voltage here at the load is 0 degrees, right? Who asked that question?
I asked that. Brooke did.
All right, Brooke, did that answer your question?
Kind of.
Help
So it's
me
just
help
the
you.
inverse.
The
It's
inverse,
the inverse
cosine
cosine
gives
of-
you the inverse cosine gives you the angle, but it doesn't give you the sine of the angle, does it? The sine comes from knowledge of lag or lead. Lag would be a negative sign associated with the angle with the current. Lead would be a positive sign, right?
Yes. Okay, I got it now. That makes sense.
All
Thank
right,
you.
now since you asked this, I'm going to do this. Just suppose, we'll get back to this problem, Jessica. Suppose this wasn't at 0 degrees. This is a dirty trick by Baginski, right? This would be horrendous because you didn't show it. Well, I'm showing. Suppose I made this 10 degrees, not 0 degrees. Got it?
What you're writing
Every-
down is just out of frame.
All right, well, suppose I made this 10 degrees, 480 at 10 degrees, not 0 degrees. Then what would the angle be here? Well, remember when you take the inverse cosine, you get theta v minus theta I, but not the proper sign. Remember this, if it's lagging, whatever theta v is, theta I would be less that angular difference, right? So
Negative 15.
the angle is 25.842 degrees. Hang on. Hold on for 1 second. Oh, I thought it was. No. Listen, sorry about that. If the angular difference here was 10 degrees, and I hope you can see this right here, if that's 10, then the angle on the current has to be less 25.842, right? So this would be 15.842. Does that make sense to everybody? How many see this? Some affirmation. There's a difference, right? If the angle here is 0, then the angle here is just minus 25.842. If the angle here is 10, the angle here is 15.842 and so forth. Got it, everyone? It's the angular difference. You're looking at me like I'm trying to cheat you. I'm not. I'm trying to be very honest with you.
Why is it positive? Why would it be positive, not negative 15?
All right, let's take it from the top. VRMS, all right, is equal to 480 at an angle of 10 degrees, right?
Yeah.
Now, I know the power factor difference in the two angles, minus 25.842, right?
Yeah.
All right, so how do I get the angle with the current? I would be what? Would be magnitude of 370, right? 0.37, right? Angle is what? This minus 25.842 would be the angle, which would be minus 15.842, right? That means the difference of these two is 25.842. All right, everybody, guys, with me? How many
Look
got
up the
that?
function you were looking for. A cosine D, or A cos D.
For real?
Yeah.
But that's not for the angle of a, I wanted not the cosine, but if I want, well, thank you, but I wanted it for if you had just like, never mind. Tell you what, thank you, Joseph. That'll be great for the cosine. That's all I need for that. So it would be A sine or A sine D for inverse sine. And that's absolutely great. But if I went, and don't worry about anything else for now. You all follow me on this part right here? This is just to show you what would happen if that was 480 at 10. All right. Now, forget that for now. Leave it at 480 at 0. Leave this current is 370.37 at minus 25.82. And let's go ahead and get VS, all right? So what is VS? Now, think about it. It's going to be what? 480 at 0, right? 480 at an angle of 0 degrees plus what? Plus this current IL, both magnitude and angle, right? Just like before, times the line impedance, which is 0.1 plus J 0.2. Do you all agree with that? Class?
Yeah.
Okay. And I'll do this. This is more like a workshop than it is an actual formal lecture, but it will help, I think, help everybody. And I'm going to go back here. So then I'm going to say VS. First, my IL. What do I have for this? Oh, I didn't put that in there, did I? I didn't. So is equal to 370.37 times EXP to the 1J times A cosine, oops, minus this. This is where you guys can yell at me. Minus that A cosine of 0.9, right? So this should be the real and imaginary part of the current, if you can check yourself. Do you agree with that, class? Y'all see it?
Yeah.
Next, after that, I need the actual source voltage, Vs. And I can see Vs here is equal to 480 plus, and then it's going to be that line, which is I in my case, times 0.1 plus 1J times 0.2. And again, I'm using octave. Your calculators will probably do this a lot faster. So that's what I got for the for Vs in terms of a real and imaginary part. Do you all agree with that? Did you all get that?
Yeah.
I can get ABS.
My
of it too.
calculator
Anybody
goes
else?
straight from real and imaginary to angle and magnitude.
All right, now here's the one I wanted. When I get the angle, thank you for that cosine business. If I get ANGLE of VS, I would like it to just be in radians. I mean, sorry, in degrees, but it's not. Maybe, I'm just gonna leave it this. I have to multiply by 180. If you can find that, it'd be great. So it's 5.24 degrees, but it's positive, isn't it? Y'all agree with that?
29, right? Yeah.
2894
Yeah.
degrees. All right, now that is the angle associated with the line voltage, right? And here I'm going to move out of here. So if you look at the angular difference at the load, right? When I take a look at this at theta V minus theta I got the angle at the load at 5.2894, right? Minus, and then it's going to be the angle associated with the current. Well, the current is what? That's minus 25.842, right? Y'all follow me on this? All right, what's that difference? You got to add them up. It's what? It's going to be 30 something, isn't it?
Yeah.
I mean, go ahead and do the math on this. It's going to be, I don't know exactly what it is, but it comes out to what? 31.7 about. Do you agree with that, class? How many see this right here? Right, we're at it. Thank you, Jen. And what do I need to get the power factor then? I've got the angular difference. What do I do?
31.04.
Okay, 04. Thank you. What do I do to get the power factor from at the source?
Take the cosine.
Exactly. Take the cosine of this. Thank you, man. So I just take the cosine of that. Could somebody give me that? And you can check the answer. Cosine of that 31.04 is what degrees?
1.14. I'm sorry, I missed the. No.
Anyone?
0.85, 86.
0.86 is the power factor at the source. Y'all follow me? You with me on this? Okay. Are we good? I'm just about out of time too, unfortunately, but I wanted to do these. So are there any questions before we move on? We're going to break out of here. How many people do we finally have here? 40. Oh, and they're going down quickly because I use that word break out of here. All right. Well, if you got to go, you got to go. I still got a minute left though. 39. It's going down. Are you with me? What I've done?
Yeah, but it's kind of different from what the solution says. Like the
What is
final
the
answer.
solution? What do they say?
Yeah, on the solution, you have 0.996 and the angle is 5.29. So I don't know what we did wrong.
You mean for the, oh, you're talking about for the angle associated with VS?
Yes.
I'll level with you. It's probably just rounding error.
Okay.
I mean, my angle is what, 5.2894? I mean, that's close. Come on.
Yeah.
I'll
but
admit,
How many decimals should we be keeping during our calculations?
They say 2 significant decimal places or 2 significant digits, but frankly, on these kind of problems, it's very apparent. If you miss big. It's not going to be like a 0.01% difference.
But no, like
Can I-
our power factor here is 0.86, right? The power factor in the solution is 0.996. So
Hold it.
it's okay.
Is that the same problem?
Yeah, it's 5.31.
All right, now I'll tell you why I know there's something funny about that. You see this right here?
Mhm.
I know the power factor for just this without anything else in the circuit will just be the cosine of the angle between these two. So if you take the inverse tan of 0.2 over 0.1, which is really 2, inverse tan of 2, get the angle, then take the cosine of that. That will be the power factor on that. That thing's much greater than 0.9. It's an angle much bigger. So adding this losses to this will decrease the total power factor. I guarantee you. This answer is reasonable, that we got 0.86 is reasonable. It should go in that direction, not the other, because this is lagging, isn't it? Right?
Yeah.
It says, if that's lagging, this is lagging, the power factor will get worse, not better. I don't know what problem you're looking at. You're looking at 3-1 solution?
No, 5.31.
Yeah, I mean, 5.31.
Yeah.
That's incorrect. I can
So
tell
it's
you
wrong.
that.
The solution is wrong?
I'm telling you what, if I haven't looked at it, but there's
Yeah,
no way
the
that
same
power
power
factor can be
factor
better.
there is 0.996.
I'm going to have to look at it. It's not correct. This is the right way to do it, right
Okay.
here. All right. Let me continue on with one thing. I know we're in an office hour now, so if you need to go, you can go. This is where I was going, and I'm going to even ask you to go ahead and read through this. We're going to be talking about something called complex power, and I'm going to just mention this. It's not part of the quiz. You're going to get that question over again, but it's important, and it actually makes the quiz easier doing it this way. So here's something. It's called complex power in this book, and it's also, I don't know where it is in yours, but this book does it easy. Complex power is S. Now that's a symbol. The minute you say complex power, people think it gets worse. It actually gets better and easier. Complex power for any impedance or anything is just the voltage associated with that anything times the IRMS, or the current going into that anything conjugated. You hear me? Now, let me show you why that's so easy and makes things so nice. So, suppose I have something here, a load. Now, this is an office hour, but I'm going to tell you, it'll help you. And I know I've got 16 participants right now. So here we're going to have a current going in, I'll call it I
Page
line.
up a little bit.
Yeah, we're going to have a current going in this. This is the load. It can be anything. And say I line is just some I naught here at an angle theta I. It can be plus or minus, it doesn't matter. Here we're going to have a voltage across this load. And that's going to be some V0 at some angle theta V. You got it? A voltage and a current. Now the complex power associated with this is S. And S is equal to V load times I going into their load conjugated. You'll notice the I is going into the positive terminal. And I know we had that outage, short outage here, so just bear with me.
What are the
Now,
symbols for S and I?
this is a conjugation. The star, how many have heard of conjugation before? Y'all with me? Jessica, you have, right? And so have you, John and Matthew. Are you with me? So if we're talking about V times I conjugate, there's V, just repeat it. It's V0 at an angle theta V. I conjugate will be times I0. Conjugation means you take the angle and you make it negative. So it'd be at an angle of minus theta I, right?
All right.
Now, if you look at this, that means you've got V times I, or V naught times I naught. And then the angle is simply theta V minus theta I, correct? And that is the complex power. Now, here's why it's so nice, and it saves you so much work. Gosh, I wish this thing didn't have that outage. When you plot this, this is going to be in the S complex domain, right here. This is going to be the real power. The units are watts or kilowatts. This is something called the apparent power, or a reactive power, pardon me. This is the reactive power. And what you end up doing is taking this value, it's got a magnitude here of V naught times I naught. That's the magnitude out to here. This angle is theta V minus theta I. Now, here's where it's nice. Remember, do you all agree you can get this value and this value, current and voltage, very easily? Think about your basic circuit analysis. If you have a voltage and you want current, you take the voltage and divide it by the impedance, you got the current, right? Very easy to do. Now, here's why it's so easy, so nice. If you take the projection of this here, that is the actual power that's used. It's the real power. All right. So if you take the cosine of theta V minus theta I times this V naught I naught, which is a scalar value, you get this. This portion on this axis here, that is called the reactive power. And this is complex S. Now, I don't have time right now to show you how it makes things easier. But the beautiful thing about this is the sum of all the powers supplied and used in a circuit is zero, complex power. And it will make a lot of the calculations easier. I'm going to give you, in the PowerPoint I gave you, I'll mention some of the things you can look at. And we can use this to do problems. I have things I can show you, but I'm going to just tell you this right now, that I don't have enough people here to do what I want to do. But I can tell you what we're going to do with this. We're going to find a clever way, if this is given, you know, what we'd like is what? We'd like this power factor, the difference, to go to zero. So the cosine of that would be zero and the power factor would be one, right? That's the ideal. And the way we do that is by adding a capacitor in parallel. For me to do that, though, I prefer to have the whole class here working these problems. And I know today was kind of an awkward thing because of that failure. And I don't know, I have no idea what happened. I was talking 1 second and looking and everybody's frozen. And did you guys have to log back on to Canvas or not?
No, we never got booted from the meeting.
Well, I did. Maybe somebody figured out a way to boot me. But I'll tell you, we're going to be doing problems 534 through 542 next time, going through it. But I need to go through the theory because the complex power will make a lot of this easier to see. You'll see how you can deal with things. And then we go into something called three-phase power. Now, as far as the quiz, does anybody have any other questions regarding the quiz Monday, any of the problems, anything like that? And I can look at the solutions, Jessica, to just see if what you said is true, or it's hard for me to believe Irwin's solutions manual is wrong there, but it could be. I mean, he is not.
Not the same as what we did in class.
What's that?
I said it's not the same as the one as what we did.
Yeah, I'm going to see what he's got here. That's 31, right?
Yes.
Let me see. I mean, he's a human being. He's fallible too. All right, let's see. Oh, he's using complex power. So that's complex power right here. He's taking V times I, but really, here's his 160 kW is the real power. This is the reactive power. He calls it Q. All right. And then, so he gets this. He gets a 77 here. All right. Then he gets this complex power. And I want to tell you, see that 77.45 there, Jessica? That should have a J in front of it.
Mm-mm.
That's the one thing I see. He does have it right here. There should be a J here, but he has the KVA. So that, in fact, maybe you don't need a J, but I'd put a J there. Then he gets S is equal to V times I conjugate. Yeah, that's right. He's got the right value for I. Oh, I'm sorry, that's Z. No, that's I. Pardon me, that's I. And then he goes ahead. Wait. Oh, it's lagging. Then I did something wrong here, I think. Let me just pull that up and see. When I said, you know what, where's this? That's the right I, right? Yeah. When I take VS is 480 plus I times point. So does he give you VS or no? Let me see. He's got 5.29. You know what he did? He just took the cosine of 5.29. What he didn't do was take the angular difference between that and the actual current. That's how you get power factor. You see that?
Yeah.
He forgot to subtract off the angle at the current.
Mm.
He made a mistake. I'll tell Dave Irwin that. I'm surprised. He almost never makes mistakes. That's wrong though.
Okay.
You are absolutely right. I wonder if I can edit that. How would I do that? Let me see. There should be tools up here to do this. I think I can do this. Where is this? That won't do it. Is it organized? I want to get that, those tools that come up. Maybe this will do it. So this should be, can I do it here? I'm going to put 29 minus, what's the angle with the current? 20, so it's minus a minus 25.84.
Yeah.
And what's the value for that again? It's 0.86 about, right?
Yeah. Mhm.
86. I'm going to leave it at that and see if this, in fact, will save it. Hopefully it will. I appreciate that. But that's the way to do it. And that should make sense to you.
Mm.
See if it saved it on your end. Okay. This is wrong. Okay. All right, other questions?
I've got a list of the octave trig functions open if you want to ask me.
It's not trig though. What I want to do is this. I'll show you exactly what I want. See this? If I have like, look at I right here. See how I has a real and imaginary part?
Yeah.
What I would want is, I would want the angle. So I type in angle of I, and I would want that in degrees. So if I put, I thought maybe a D here would do it. Doesn't do it. DG, no. So that's,
Try rec to polar, like REG or REC, the letter 2 POL.
it's rect to POL, right?
Yeah.
I'll tell you what. I'll work on that later, but that's the essence. Jessica, do you have any more questions about this? Or Joseph?
No, sir. That's,
What?
no, no, no.
No, you're good. You guys can go. Enjoy your Friday. It's going to be wet today and tomorrow. I don't think you're going to go. If you're going to the game, I hope you have a good umbrella.
Yeah.
Is anybody
No.
going to the game? Now the class is basically gone. No?
No. Too much risk,
What-
too much trouble.
Yeah.
What time is the game, by the way? Anybody? Hey, wait a second. There's a tennis. I want to go watch the rest of the French Open. Djokovic is playing Tsitsipas right now. So, you guys have any more questions? 'Cause I'm going to cut out of here. No?
No.
All right. Have a great weekend. Enjoy. Sorry I can't stay longer, but there's no reason to. All right, guys. Take care. Have a great one.
Bye-bye.